This video is a continuation of the functions notebook and will discuss recursion, short circuit evaluation, and lazy evaluation. Recursion is a tool that we can use to solve certain types of problems, where the complete solution depends on the solutions to smaller instances of the same problems, and it's realized by a function directly or indirectly calling itself. Now, typically recursion is not included in introductory material, but we feel it's an important enough topic that we should at least introduce it. And on top of that, it's really an excellent way for you to practice and understand scoping rules and function environments. So we're going to begin with a non-recursive solution to computing a factorial. That is, n factorial is defined to be the product of all integers from 1 to n. So we can write a function using a for loop to do this for any integer n greater or equal to 1. So we're going to call our function fact1, and it's going to take a single integer n. In this example, to keep it simple, we are going to assume that n is positive non-zero, meaning that n is greater or equal to 1. And then to compute the product from 1 to n, we're going to start with the value 1, store that in a variable called result, and then use a for loop to multiply the current result with the next integer in the sequence from 1 to n. And once this loop finishes, we're simply going to return the result. And now, of course, we can call the function and pass some integer to compute the factorial. And of course, you can verify that 6 factorial, or 6 times 5 times 4 times 3 times 2 times 1, is 720. Now, the reason that we're using factorial as an example here is that, one, it's a very simple thing to verify, even without code for small integers. And two, it can be easily rewritten as a recursive function. N factorial is the product of n times n minus 1 times n minus 2 and so on. And this is really the same thing as writing n times n minus 1 factorial. So this can be realized with a recursive function. We're going to call the recursive version of this function fact2, and it's also going to take a single argument n. And then just as I said, this is going to return n times fact2 of n minus 1, or n minus 1 factorial. And you can see in the description above, the formula is written there as well. So the call to fact2 inside of fact2 is the recursive step. And this is going to return the solution of the smaller problem, n minus 1 factorial. If we were actually to call this function, fact2, as it's currently written, it would run forever, because there's really nothing here that tells the function when it should quit. It continually subtracts 1 from the current value of n, and then calls itself again. Now, in reality, this would eventually fail and cause an error, because the machine running it does not have an infinite amount of memory to hold the entire stack of function calls that would result. So how do we fix this? Basically, we need an instance of the problem that we can solve without recursion. And this is called a base case. Base cases are non-recursive solutions to very simple problems that allow us to exit or stop recursion when these very simple cases are found. So for this problem, we know that the factorial of 1 is 1. So we can actually check if n is 1 prior to any recursive call and simply return the solution when we find that case. So we're going to add an if statement that checks if n is equal to 1 to handle this base case. And when it finds it, of course, all it has to do is return the value 1. Now, this function will actually stop calling itself recursively when n gets down to the value 1. So if we now call our function, passing the same argument as we did before, we see that we get the same result using the recursive formulation rather than the explicit loop. So to recap here, recursion is a very powerful tool that can help us to write simple functions to accomplish sometimes very complex tasks. We've already had some discussion on R's lazy evaluation of function arguments, where if we have two arguments to a function, but only one of them is actually used within the function, the unused argument is never evaluated. And so to see this again more concretely, let's first define two functions. Each of these will simply print out their name and then return a unique integer. So f1 here will print f1 and then return the value 1. And then the function f2 will print f2 and return the value 2. And then we're going to write a function f. And this function is going to take two arguments, a and b, and it's going to print the second argument, leaving the first argument completely unused. And now if we call our function f, and as arguments we pass the output of f1 and f2, that is the result of calling the functions f1 and f2, we see in the output that only the function f2 was called. The first line of the output is the print from the function f2, and the second line of the output is the call to the print function inside the function f, or it writes the value of the argument b. The function f never used the argument a, and because of R's lazy evaluation, the function f1 was never called. And so we've already seen a couple examples of this, but similar behavior also occurs with Boolean operators and OR. There are cases where a solution to the Boolean expression is known before all the operands are even considered. For example, if you remember your truth tables for and OR, if the first argument to an AND expression is false, then we know going in that the whole AND expression will evaluate to be false. And likewise, if the first argument to an OR expression is true, then we know that the whole OR expression will be true as well. So in these cases, there's really no need to evaluate the remaining argument, since the outcome of the expression is already known. And in fact, the skipping of the evaluation of the second argument is commonly referred to as a short circuit evaluation. And this is actually what we're going to take a look at now. So we're going to copy our two helper functions from before, but we're going to change the return values from the integers 1 and 2 to the booleans true and false. And then to test this, let's print out the result of an OR expression using these two functions for the operands. Now in the output, we can see that f1 was called, but f2 was not. And the reason for this is, after the evaluation of f1, the first operand to the OR expression, R was able to determine that the entire expression would be true because the return value of f1 was true. And so there was no need to evaluate f2, and it did not. If we do this again for an AND expression, we see that both functions are evaluated. And this is because a single true value returned from f1 is not enough to determine the outcome of the entire AND expression. The return value of f2 also needed to be considered. If we were to swap the order of the operands, we would see different behavior for both and OR. So in this case, because f2 returned false, the OR expression was forced to evaluate both operands, f2 and f1. And with the AND statement, the false value returned from f2 was enough to determine the result of the entire expression. So if your functions have side effects, right, in this case, we're simply printing to the console, and in certain cases, we did not see that output. But maybe your functions are writing to files or manipulating the environment or doing whatever, and you don't want those functions to be skipped, then you really need to pay attention to places like this where either short-circuiting or lazy evaluation may occur. On the other hand, you can take advantage of short-circuit and lazy evaluation to make your code more efficient. For example, if you knew that a particular function returns true more often than not, then perhaps you make it the first argument in an OR statement. Or perhaps organize your code such that the simpler or faster functions are considered first, in the hopes that the result allows R to avoid more complicated or slower functions. Of course, mileage may vary here, and this will be something ultimately that you have to test and evaluate for your particular problem in code. To wrap up this notebook, I do want to remind you that the built-in help can be used for everything we covered. Simply type help in the function name for a full description. If you only need a reminder of the arguments, you can use the args function or the structure function, both here at the end of this first paragraph. You can also check out the R for data science and advanced R links here at the bottom for more details on everything we've discussed and much more. And also, one last thing I would like to point out is that when you start to write your own functions, please make sure you're using appropriate comments. And if you want to have your functions included in the built-in help, then you can check out the link here for RD tags or R documentation tags, as well as for R Oxygen 2.